Hello, good evening, everyone. A very warm welcome to XP Teachers Live Session 2. We are thrilled to have you all here as we dive into a crucial aspect of teaching, which is mastering concept teaching. And today we have joined two wonderful experts who bring deep experience and practical wisdom to the table. We have Mr. Goutham BS, he's a head of training at SciKraft, and we have Ms. Vidya B R, principal trained at SciKraft. Also, before we start our session, a gentle reminder for those who are using phones and mobile users. If the speaker window appears zoomed in, you can simply pinch and zoom out on your screen to get the better view. And let's start. Over to you, Gautam.
Thank you, Aparna. Hope I'm audible.
Yes, you are.
Thank you. Welcome all of you to the second episode of XP Teachers Live. The intent behind the program is to set up a peer group for teachers to discuss a multitude of pedagogical issues. And more so than ever, it is very important now that we teachers come together as a community to discuss various of these ideas and topics so that we can affect a positive change in the way we deal in our classrooms. And in this particular session, we will be convergently focusing on the idea of concept teaching, which seemingly is an extremely important issue that concerns all of us. And in fact, introspectively, when I look back upon my teaching days, one thing that kind of stood out is that students were always able to state or define a bunch of theorems or principles, but they lacked an insight into it. So most of the times we find children to lack deeper insight into laws and theorems that they learn. And I want to start this conversation with this question. The first one is to find out if some of you are also facing similar issues where the children are able to state laws, principles, and theorems, but when it comes to applying these laws, principles, and theorems to solving problems or addressing a situation, they kind of are stuck. Do you people also kind of face similar issues? Let us start with that question. If I may get some responses from the audience, maybe some thumbs up if you are facing such issues in your classrooms. Yeah, we have a few responses here. And it is a very common issue that I see. And I want to pose this question to you, Vidya. How much of this issue is concerning with the way the content is delivered in the classroom?
I would say 90%, because all children are not same. The way it is delivered now might have reached 10% of children, but it is not reaching the rest 90%, maybe because of the process. So if we focus more on the process of learning, then the internalization of the idea will be better by children, and then they will be able to apply it in a real situation. So that's what I feel.
So if we were to come up with suitable ways of delivering various content that is part of the curriculum or even if otherwise, should we start with categorizing content into different brackets? And if that is the effort we have to make, then what are the available templates for it?
Yeah, that's a very good idea. And I always believe in categorizing content so that it helps me plan my lesson better. It starts from setting of the objective to achieving whatever is the objective set for the lesson. So categorizing content, especially in science and maths, helps us a lot. Therefore, it plays a very important role. Now let us see what are the content categories available in science and maths. In science and maths, the content can be categorized into 4 categories. As you can see, it is facts, concepts, laws or principles, and procedures. Now we will get into detailing of each of these categories. Talking about facts. Facts are nothing but occurrences in the real world. So it is something real, which are proved to be correct. And the test for statement of any fact is verifiability. It can be verified. For example, water boils at 100 degrees centigrade is a fact. The boiling point of water is 100 degrees centigrade is a fact. Whereas boiling point itself is a concept. So we'll talk about it when we talk about concepts. So this is what facts mean. This is how we can identify facts in our curriculum, science or maths curriculum, whatever grade, wherever we are dealing with. Now, if we see these ideas, if they have all these attributes, then that content can be categorized as facts. Now let us move on to what are concepts. Concepts are nothing but generalization formed through observation and classification or classifying examples which have common characteristics. So if a set of examples have common attributes, they can be classified under or it will develop a generalization with those attributes, and they are called concepts. And there is a beautiful structure given to a concept by Brunner. What he says is concept will have a name, concept will have definition, concept will have attributes, concept will have examples, concept will also have non-examples. And the way we categorize any set of examples is based on the similar attributes they have. So we identify the similar attributes through observation. Then we put all of them together in a hierarchical manner with whatever is important, then goes the rest, because the second one should follow first attribute. So this is how a definition for a concept is formed.
I mean, there should be a certain chronology in which the attributes
there should be a chronology in which the attribute should be defined in a definition, or it should be put in a chronological order, and it will be given a name. That the name is, I mean, all of us to be on the same page universally.
So can you give us an example for a concept?
Yeah, example for a concept will be anything like tree. Tree is a concept. The tree has a name. The name is tree. The attributes of tree is it is a living thing. It has parts of a plant, that is, it has stem, roots, and leaves. It can synthesize its own food. But another attribute for a tree is it has a larger stem, and the stem is barky in nature. So if any plant has these characteristics, then we can classify it under tree and given a name tree. So tree is a concept.
How about features such as the type of leaves on a tree? Does it count into the attributes? Or?
For overarching idea of tree, the type of leaves will not matter. If a plant has leaves, stem, and roots, and the type of stem, that is, it is large and it is barky in nature, will fall under tree. That becomes a non-essential attribute. But if we make that as an essential attribute, then our classification can be further made. So it will fall under another category.
So how about identifying laws or principles, and how about identifying procedures? What are the attributes?
Yeah. Principles are statements that articulate rules or relationships that can be applied to a specific situation. More so, it is a relationship between two or more concepts. We'll keep it as easy as that. Procedures, laws are nothing but it's a relationship between two or more concepts. For example, Archimedes' principle is a principle where we are establishing a relationship between buoyancy and density. So all this, when it is related, and it is given in the form of a statement, and this idea can be applied in a specific situation, then it is called a principle. So Archimedes' principle is a classic example for principle. Newton's laws is an example for principle, and the theorem which states the sum of three angles of a triangle is also a principle or rule or generalization.
And how about identifying procedures?
Procedures,
I think it is kind of self-explanatory, but then
I know. Procedure is nothing but it identifies the steps in which an action has to be followed. Action meaning a process. Suppose you have to write or you have to conduct an experiment. You should have a procedure, step-by-step procedure. The first step should follow second step. We can't do step 5 and come to step 5. So there is a logical sequencing of doing a process, and that is called a procedure. Like construction of a triangle. conducting an experiment. All this comes under procedure, or plotting graphs.
And to what extent does this classification have an effect on the way such content is delivered in the classroom?
Yeah, that plays a very important role because it helps us to plan our lesson so that we can select appropriate pedagogical approaches depending on the age of the children and the type of content. Suppose if I have to deliver few facts in my class, then I can simply present facts. So that is the way I deliver facts. If I have to deliver concepts, then there is a way in which I have to deliver concepts, because concept will have all this. And concept is developed in as a model in our mind. So a mental model is developed, and there is a process in which the mental model is developed. And that is also very beautifully given by Brunner. We can see that the mental model is developed in 3 stages. That is enactive mode, iconic mode, and symbolic mode. As you can see on the screen, enactive mode is a phase where we are not exposed to that idea before, and we are exposed to a new idea at that time, and which requires concrete experiences. Suppose I have to teach addition to a 4-year or 5-year-old child. I simply cannot say 3 plus 3. Then I have to help the child know for 3 beats or 3 more beats, 3 more chocolates, so that the child will know the quantity is increasing by adding 2 or 3 more to whatever set it already had. And it will also know that there were 3 chocolates, and adding 3 more became 4, 5, and 6 chocolates. So this is how addition is taught in an enactive mode, when the child is learning for the first time, and it requires the concrete experiences, and it is also real. Then once this is done for a period of time, the child would have developed a mental model for addition. Suppose a child can visualize addition in the form of steps. When I say 3 plus 3, the child might visualize going up 3 steps and going up another 3 steps, which adds on to 6. Some might imagine it to be lines, 3 lines plus 3 lines. So at this stage, we don't need to give an experience which is hands-on or concrete. Then once this mental model is developed, the child will go on to symbolizing this in the form of language or numbers. So this is the 3rd stage, where the child will develop a mental model in the form of symbols. So that is, as the child matures in learning and also by age, the child would have reached symbolic mode. So once we know the process or how the models of teaching is developed, this will actually help us to select appropriate learning experiences to be provided to the children. And it will also
I'm sorry, I think we had a brief network issue. Am I audible?
Yes, you are.
Yeah, sorry. Sorry for the brief network issue. I think for a while we'll turn our camera off so that the discussion is not interrupted. There seems to be a little issue over here. And Vidya, one question that I wanted to ask is, how much of this learning modes is age specific, and how much of it is something that is applicable to all ages? So is it that children of different age categories fall under these different categories, or is it that whenever someone comes by something new, there are these stages innately someone has to follow?
It is not age specific, and it is also age specific. It depends on what experiences the child has gone through. If the child has seen something, then we need not give a learning experience in an adaptive mode. But if the child has not seen, or a man of 40 years has not seen something, has not experienced something, then the process starts from inactive mode. And it's always good to start from inactive mode for a concrete mental model of that concept to be developed in anyone's mind.
And when we talk about these modes, how do we zero in on a particular mode? Is it based on the nature of the content? Like, let's say I have to deliver a concept. Then what are the considerations I'll have to make to find out if I should deliver it in an inactive mode, anchoric mode, or a symbolic mode?
That depends on the types of concepts. Again, there is another classification for concepts, which says there are different types of concepts. If you can see that, there are two types of classification for these concepts. The type 1 says that there are two types, that is concrete and abstract, and classification 2 is given by Brunner. It has 3 types. Now let us talk about classification type 1, which has 2 types of concepts, that is concrete concepts. Concrete concepts are those which are perceived to an individual through stimuli, that is any of the sensory stimuli. For example, fruit, for example, vegetable, all these are concrete concepts. Whereas when we talk about abstract concepts are also defined, but the concept is not directly perceived by any sensory stimuli, but the effect or impact of something is perceived to define a concept. For example, momentum, for example, density, all these are abstract concepts. So when we have to give these concrete experiences, the children should be, that again is age specific, or if it is for the first time. And abstract concepts needs to be developed at a later stage. If you have gone through Piaget's stages of development, then all these make sense. The concrete operational stage is the stage where we have to provide concrete experiences. Formal operational stage is the stage where we can provide abstract experiences, or abstract concepts can be developed.
Can you give us a couple of examples for concrete and abstract concepts?
Yeah, concrete concepts, as I told you, vegetable, fruit, conductors, insulators are all concrete experiences, the materials.
Meaning
magnetic
those examples
materials,
which
we can actually
easily conceive.
Can be conceived through sensory perception,
Okay.
sensory stimuli. Abstract are those which cannot be perceived.
An example for it?
Momentum. Momentum we can't see, touch, feel, but we can see the effect of something which is an impact. That impact can be felt and the momentum can be defined.
But there is something that I still use a sensory perspective to feel. Is there something that is beyond sensory perspectives as an example that we can take for abstract?
Abstract is time. Time is a concept. It exists, but we cannot actually see or feel time. And structure of atom. The structure of atom is beautifully defined, but nobody has actually felt or seen structure of atom. It does not come to our sensory perception.
So, these two methods of classification, are they kind of different from each other, or are there overlaps?
There are overlaps. For easy transaction in classroom, if I cannot see what is happening at the other side of wall, we can take or sit on shoulder of somebody. So Brunner's model, we can sit on Brunner's shoulder to see what is the other side of the wall. And this classification helps us in identifying concepts in a different way and transacting in a particular way in the classroom.
Can you give us an elaboration on the Brunner's model where we have this selective, distinctive, and relational?
Yeah, definitely. I would love to. See, Brunner has classified concept in 3 categories. One is conjunctive concept, disjunctive concepts, and relational concepts. Conjunctive concepts are those concepts are defined in such a way that all the attributes or essential attributes must be present. Suppose I take an example of triangle. Triangle is a concept. It has a name. It has a definition. It has examples. It has non-examples. So the structure, it has fit into that structure. Now let us see whether it fits into the structure of conjunctive concept. Conjunctive concept, the triangle, the attributes of triangle is, it should have 3 line segments. It should be a closed figure. All 3 line segments should meet at their endpoints. it should form 3 vertices and 3 angles. Either out of these 7 attributes, even if one attribute is missing, then it won't be a triangle. So all the attributes are must, and when we define, all the attributes are connected or joined through an and. So it's a must. Such concepts are called conjunctive concepts. So if I define a hierarchically all these attributes, triangle is a closed figure. It has 3 line segments. 3 line segments meet at their endpoints to form 3 vertices and 3 angles. Such a closed figure is called a triangle. Example of triangle: scalene, right angle triangle, obtuse angle triangle, and non-example for a triangle is a square. So it fits into the structure and the requirement of a conjunctive concept.
And how about for disjunctive?
Yeah, disjunctive is similar to this, but here the attributes may be this or something else. So it is not a must and it's not and it's or. So if I have to give an example, polygon is an example for disjunctive concept. Polygon is again, the attributes will be, it is a closed figure. It will have 3 or more line segments which meet at their endpoints. But here the number of line segments are, if it is 3, it becomes a triangle, or if it is 4, it is a rectangle or a square, or if it is 5, it becomes a pentagon. So that falls under disjunctive concept.
How about for relational?
Relational concept can be easily defined for example, density, where density is a relation between mass and volume. Therefore, there is a relationship between mass and volume, or there is a relationship between density and volume, density and mass. So such a kind of concept is called relational concept.
And can we adopt to a common way of delivering these various categories of concepts, or are there some methods that better suit each of these concept varieties?
Yeah, there are some. Today I would like to talk about 2 types of methods or approaches which suit very well for these types of concepts. For example, if there is an approach called inductive deductive approach, where we have 2 types of logics working there. One is the inductive logic, the other one is the deductive logic. Combined together, they form an inductive deductive approach. And how does this approach work? Suppose if we take example of a conjunctive concept, that is triangle, if I have to deliver that, inductive deductive works wonders in class. So how do we plan that lesson? What is the way in which we can deliver? For that, in induction, what we do is, we give a set of examples. So it is examples to generalization. Unlike deductively, what normally all these days what we were doing is, we would call out the generalization and give out some examples. Here we give a set of examples where children will identify the attributes. They come up with the generalization. So it is examples to generalization. So by giving a set of examples, children will identify all the attributes required for a triangle. That is, it is a closed figure. It is 3 line segments, 3 vertices, 3 angles. And they form a statement which can be rephrased and reframed by teacher and given a name to that concept as triangle. And deduction is the method. Once this generalization is done by students, now we can also test and verify whether the children have actually perceived the idea of triangle. Now if I show a square or write a square on the blackboard and ask children what is it a triangle, then they should say it is not a triangle. So by giving a non-example, we are actually deducing, or we are using a deductive logic to make sure that the concept is perceived rightly in the children's mind. So that is called inductive deductive approach. There is one more method which is called concept attainment model. That is again a very beautiful methodology or approach which can be used to develop a concept. For that, disjunctive concepts can be taught using concept attainment model. In concept attainment model, what we do is, there is a syntax. In that syntax, what we do is we present set of yes and no examples. Yes examples are the examples for which the children will identify the attributes and develop the new idea or concept. And no examples are those examples which are very similar to yes examples, but they do not fall into one type of classification. So that idea is used. In phase 1, we present a set of yes and no examples, and each set of yes and no examples is presented at a time. All yes are not presented. One set of yes and no examples are presented. With that, children will identify there is some similarity and they'll hypothesize. Then teacher will present another set of yes and no examples, but it is not called out or yes or no as we did it in the first phase. In the phase 2, it is unlabeled. So children will label which are yes and which are no examples. From that, we will come to know that whatever idea they have generated is correct or not. Then the hypothesis is verified by teacher and the generalization is called out. For example, how do we do this? Polygon, if I have to teach polygon, then this it can be beautifully done. I give one set of, let's consider figures of polygon, one square, one rectangle, one triangle, as yes example. As no example, 3 lines written randomly where they don't touch each other, or it is in the form of a Z where there are 2 open ends, and 2 lines joined, the 3rd line is not joined, or 4th line is not joined. So imagine these pictures. These are all yes examples, these are all no examples. But we don't present everything together. We present first set of yes examples, that is 1 square and 3 lines, which are not joined at their vertices. So when we present this, children will not know what it is, but they will see that there is a difference between this yes and no example. Here it is closed at all ends. Here the figure is not closed. So they'll get an idea. With that, the thought process starts. Then we present the second set of example. Here we have a pentagon, and here we have a figure in the form of Z. Now again they will know that this is a closed figure as of example 1. Now they start finding similarity between first example and second example, as well as dissimilarity between the second set of examples. With that, another idea or attribute is added. Like this, when we present 3 or more sets of examples, they will identify that all yes examples are closed figures. They have 3 or more line segments, and all line segments are joined at their endpoints, and it forms a closed figure. And that generalization or hypothesis is made by the children. Now teacher will present another set of yes and no examples, but it is not labeled as yes and no. Now students will identify another set of polygons as yes examples. Now the hypothesis is verified. Now teacher will know that they have identified.
The teacher can come up with something like a set of polygons with a set of closed figures such as a circle, a semicircle.
Yes, that can be done as no. And beside those figures which are not repeated in first set of examples. Okay. So different polygons, maybe heptagon, hexagon, all those can be given. And with that, the teacher will now verify the hypothesis, what is going on in children's mind. Now, once it is verified, now teacher will call out, say, this is a closed figure, which is made up of more than 2 or 3 line segments, which are joined at their endpoints, form vertices, form n number of angles as n number of vertices. So such a closed figure is called polygon. So the name is given out by the teacher, and a beautiful definition is framed with the help of children's statement. So it is from examples to generalization again, but here the children will also classify and categorize based on similarities and dissimilarities. So this is another way or approach which helps us to develop concept. And the beauty of this concept is we can develop 2 concepts at a time. Now we discussed polygon with one set of examples. With no examples also we can have common attributes with which 2 concepts can be developed at a time. For example, set of insulators, example set of conductors. So once they identify the attributes, there is a difference, but there is similarity, conductors. There is a difference, but similarity, insulators. So one class, you can develop two concepts. So this concept material model works wonder in developing one concept or two concepts at a time.
And how about for relational concepts?
Again, we can use either of this. Either of this can be used. But here, when we establish relationship, it depends on what age the children are, where they're in an active or a symbolic mode. Once they go to higher classes, we can talk about the relationship. But suppose if I have to talk about density of the material, as we spoke, density is an example for relational concept. I can use inductive logic there. What I will do is, first I will establish the relationship between density and mass. Then I will establish by giving three examples. Then I will establish this relationship between density and volume. Then I will combine both, which establishes a relationship between density, mass, and volume. So there we can have combination of approaches. It can be illustrating with examples. It can be inductive logic. It can also be a deductive logic. But we should not establish multiple relationships at a time because it might confuse children.
And here, I wanted to kind of pull you back to your previous slide where you were speaking about the different modes of learning, enactive, iconic, and symbolic. And strictly from schooling point of view, where you were also speaking about Piaget's work on cognitive constructivism and various operational stages that the child progresses through. Which of these methods best suits, because most of us, if I'm not wrong, most of us who are in this discussion here today, we come from high schools.
Yeah.
We are people who are teaching children of grade 6, 7, 8, 9, and 10. So which of these modes best suits an environment that we are handling and an age group that we are handling? And can you also guys kind of give us reasons? And is it also important that we push our children to the other modes?
It is important. It is the responsibility of a teacher to push children from one mode to another. See, the aim of education is developing an overarching personality, not just asking them to know what conductors and insulators. That is not our aim. So as children, when they graduate from school, that is from grade 10th, we should prepare children in such a way that they are ready for formal thinking. They should have matured from concrete to formal thinking. That is when the instrumentation starts. That is when higher order learning starts. They need not be given concrete experiences every time. And they should not be stuck to a particular type of learning where they don't mature for formal thinking. So when we leave children at 10th, they should be ready for formal learning. So that is the aim. Therefore, it is important for us to push them from one mode to another mode. So when they are in 4th or 5th grade, they will be in iconic stage, iconic mode, where the children, as it is written there, the children will still draw some pictures, how they imagine what a water cycle is. But when they come to 7th or 8th, now they are able to verbally represent a water cycle in the form of a block diagram. So that is where they stand. So when they are entering 6th, they are actually entering from iconic to symbolic mode. That is where we introduce algebraic expressions. That is where we introduce language representation or mathematical representation of any language. Like in maths, a statement is converted to a mathematical representation. And we also introduce problems in physics. So that is where they are in. I think from 6th to 10th, they are in symbolic. So it can be conversational. But again, according to Piaget, their learning stages are different. When they are in 6th to 8th standard, they're still in concrete operational stage. So it's always good to give them concrete experiences. But when they are in 9th, 10th, 11th, and 12th, they are in formal operative stage. So we have to push them from concrete experiences to formal thinking. We have to give them formal or thought experiments during these years.
But is it not important that they also get an opportunity to actually experience it? Because in a conventional classroom, more so, a lot of information is transacted without much of visualization. So one of the key attributes of an active mode is that they get to feel, they get to pursue the idea in a sensory perspective. Don't you think that should be the
It
comments?
depends on the content, depth of the content. See, for a ninth grader, we need not give 3 bits and 3 bits for addition, but we can give a concrete experience for them to experience a higher order content like velocity, speed, momentum. So that can be given.
So you mean to say that though we have plenty of scope for starting our sessions with a bunch of tools, which will enable to enables us to give concrete experiences. You mean to say that it is important or kind of imperative on us that we also kind of push them to iconic and symbolic modes?
Yes, they should. They should mature. For a 10th grader, we still can't ask him to count number of beats and do things like that. Then we cannot teach them higher order mathematics or physics, which is not possible.
So with these inputs, let us also kind of take a few questions from the audience.
Okay.
Now the discussion is open. I had a few questions that I wanted to pose with you, and I'm through it. So I'll open up the podium. Are there any questions? Please feel free to open up. Let us set this up as a discussion now, so that we can diversify the perspectives here.
Do we have any questions? You can also write down your questions in the comment box as well.
Yeah, that also will do. There are a few points that I also wanted to add as part of this discussion. And one of my questions to Vidya was that is it important to push children through these different modes? And from my own experience, as I say it is very important because much of science or mathematics that is pursued beyond the limitations of a school are of abstract nature. So much of what we do, it is not as easy to bring in physical experiences as it is. So something like conductors or insulators or something like speed and velocity, it is very easy to come by plenty of examples. It is very easy to build resources to provide an actual experience of these ideas. But as we grow beyond a school, the ideas that are discussed often come by so much of abstractness.
Then we can bring in contrived experiences.
Yeah, so
may not be concrete, but contrived.
Yeah, we can bring in contrived experiences where we can present analogical models, but not the direct, direct example for something. So the ideas that are presented today more or less kind of capture a crisp overview of how one can approach concept teaching. It is very important that as an academician we enter the classrooms with a sense of and a grasp on what is being delivered, so that
and
an appropriate.
It makes our work easy and also helps us to choose an effective path to achieve the objective. So, like if I misinterpret a content category, or if I interpret a fact as a concept, how I won't be able to deliver, that also I will tell.
And in fact, the other way around is something that I find is a very prevalent problem, because at least as a teacher of science, something that I come by very often is a very factual presentation of scientific ideas. So many times when laws of nature are presented to children, they're presented in a very, very factual sense. Whereas such presentation may enable the children with the vocabulary of science, it deprives them of that insight.
Yes, insight and application. So that is when they lack to apply it in a new situation.
Yeah, so it is very important that the children get right kind of experience about the content being delivered so that they develop deeper insights. And that is what is going to translate into an applicable skill in the due course.
Correct.
So that is the difference between someone who can state Newton's laws of motion to someone who can apply it to solve a problem, to someone who can use those laws to construct a machine. And I don't think, and you may also kind of add on to this point, just by defining and articulating the laws of motion, we will not be able to inculcate these traits in children. Someone who can solve a problem will have to have the idea presented to him in a much different fashion, isn't it?
Yeah, it should not be a direct problem where you substitute particular values to a variable. That is not the idea of child solving a problem. Child should conceive the problem, analyze the problem, then synthesize how to solve that problem. So that process, if the child is able to go through, or if we present problems in such a way, then we can see that the application of learned concept is applied there.
Yeah. So with these
if
remarks,
the question is very direct, which is we're matching to the formula which the child will use, then it does not serve our purpose.
And then what kind of here, because you have brought in this differential of a child not just solving a substitution based problem, but to be able to conceive something that is more realistic and more real time. What kind of experiences will fortify this ability in children? Because that is where we find plenty of our children to lag behind, where if it is simple X and Y substitution, they are quite prevalent and they're kind of quite conveniently doing so. But when it comes to interpreting a statement.
Now, when we talk about these relational concepts, they should visualize that when the volume increases, density decreases. When mass increases, density increases. So if the learning experience, what we have provided by developing that idea is reached, it has reached children, then they will be able to visualize the relationship between many ideas, with which they'll be able to extrapolate a problem. So suppose if I'm increasing this, then this should increase or decrease. Or the direction of that might change. So if they can extrapolate it that way, that depends on how they have learned that idea. Not just substituting and finding and writing units for density.
And in this regard, how important is it for us to provide, because as you were remarking, it is very important for us to push children through different modes of concept learning. They'll have to eventually figure out or kind of make peace with learning concepts through symbolic representations or through iconic representations. But nevertheless, how much role, or if I were to put a tab on it, how much role do you think concrete experiences play in helping children grasp these frameworks better?
100%. Concrete experiences always gives sensory perception, with which the mental model is whatever model the child creates is more concrete. There will be no doubts.
So thank you, Vidya, for your inputs. And then with this, the stage is open. If there are any questions, please feel free to pose it.
And as you asked, it also depends on what is the previous experience. Our curriculum is built in such a way that it is spirally built. So one attribute is built at one stage. The attribute is added in the next grade. Multiple attributes are added over a period of time. So when we are here, we need not give a concrete experience. We can build over it. By then, the child would have come to symbolic representation, or it would have created an iconic model, or it would have been coming to symbolic idea of what the concept is. So we are only adding attributes. So this is how we can, decide what type of experience we give, whether it's iconic, symbolic, or enactive. Depends on the previous experiences also.
So, if I'm interpreting right, if there is a concept that is introduced in grade 6, and if a teacher has provided concrete experiences in grade 6, then if a few additional attributes are listed in grade 7, do you mean to say that we don't have to go through the concrete experience stage or enactive
If
stage?
that attribute can be given through concrete experience, then it's good if we give a concrete experience. If it cannot be given, then concrete experience is good.
Okay, thank you.